Okay, let's get back into stuff. So, what did the result that we just do prove? Guys, what did we just prove about CFGs and Chomsky normal form? Can any grammar be converted? Or are there some that we can leave out? Well, if we think about what each of these does, the new start variable, we can do that with any grammar. Eliminate the epsilon rules. We just keep track of what is nullable. There's a procedure to do that. And then we just add new rules depending on whether the variable was nullable or not. Eliminate unit rules, that's just copying rules up and down. We didn't have to think cleverly about that. And then steps 4 and 5, those are easy because it's just replacing the right-hand side with variables and then shortening up the right-hand sides if it's too long. So can this work with any grammar? Yeah. So we can actually convert theorem. Any CFG can be converted into CNF, into an equivalent grammar in CNF, has the same language. Okay, cool. Okay, so when we did regular languages, remember back a few weeks ago, what were the things that we dealt with regular languages? So we had regular grammars for sure, but what are the bigger things that we talked about more often with regular languages? Yeah, a DFA, NFA, that sort of thing. So we did a grammar for context-free languages. Maybe we want a machine model for it. So just like with regular languages, could we come up with a machine model for the context-free languages? So let's try to figure out, could we actually do such a thing? Well, let's see. Think about the derivations again. So when we tried to derive a string, we started with the start variable, then we applied a rule, maybe this one, and then maybe we applied another rule, say this one, and then let's say we made s disappear to make this simple. Well, at each point in this derivation right here, how many variables are in each of the pieces? Yeah, just one. So there's really no choice there of which variable to use. But in the grammar that we made for balanced curly brackets, we had one that was unambiguous, meaning that we didn't have two different derivations that we could use, which was doing this one. And in this case, we would apply the same rule again on the inner guy. And then I'm going to shorten it for time reasons to get the string at the end. So here we avoid the ambiguity of the previous grammar because we could have multiple ways of generating the same string. However, with this grammar, what is the issue? Or sorry, with this derivation, what is more problematic than that we didn't have in the first one? Yeah, at each point, we have multiple s's to deal with, right? So now we got to figure out, oh, which s should we deal with, right? And so because it's the context-free grammar, does it actually matter which one I pick to fix? No, it doesn't matter. As long as I apply the same rule that I would have applied, but just in a different order, it doesn't matter because it's a context-free grammar. It only depends on the variable itself. But was there a way that we kind of mitigated against this? that we try to avoid this a little bit. Did we talk about a certain type of derivation that avoided the choice of which variable to pick? Yeah, the leftmost derivations. So the leftmost derivations we talked about, we always picked the leftmost variable. So there was no choice of what variable to pick, which is cool. Great. So let's think about this a little bit more. If I want a machine model, so like a DFA or NFA, I want to make them as close to a DFA, but it'll be like an NFA. Let's just think NFA. I want it to be close to an NFA, but clearly it can't just be an NFA because we want to get some non-regular languages because some context-free languages are not regular. So we can't just stick with an NFA. We got to put more into this. But with a machine model, I want it as close to an NFA as we can. So how does an NFA read a string? In what order does it read a string? Yeah, it proceeds forward. Maybe it doesn't read a character on a transition, but it moves forward through the string and never goes back. Well, think of leftmost derivations again. Suppose that we have a derivation going, we're trying to do a leftmost one, and here's a variable. And let's just assume that this guy is the leftmost variable. There isn't one to the left of that variable. What does appear to the left of that variable? Yeah, it's just terminals all the way down. It's turtles all the way down, terminals all the way down. Okay. Yeah. So it's all terminals over here. Well, if we have terminals appearing only there, will they ever change for a context-free grammar? No. So if you think about it, then if we want this from a machine model's perspective, then maybe we can have the machine try to apply the rules in some way so that what is produced on the front, the terminals on the front, those can be consumed by the machine, can be read off of the input. And then if it encounters a variable next, then it can apply a rule and then deal with the terminals that appear and then go to the leftmost variable. So because every derivation has a corresponding leftmost derivation, I think we have a shot here because we only have terminals to work with and we can just have whatever the machine is, read those off of the front there. Great. But let's think about it a little bit more. What should we add to the NFA to make it useful for the context-free languages? What possible data structure or storage mechanism can we have? We can't have it say it has a fixed size of what you can add to this structure. Because if it has a fixed size, I could have just add those in the states. And I can add as many states as I want as long as I have a finite number. So whatever we add, it must have an arbitrarily large size. We better be able to add as much as we want into it so that we can grow it or shrink it as the case may be. Okay, well, let's see. Well, think about this variable for a second. And let's just say it has a right-hand side that is really long. So like B, C, D, E, F, G, H or something. So then if we apply the rule, we still got terminals over here, so that didn't change. But the derivation's length grew longer. Where the things on the right are still the same. Well, let's see. Well, we gotta have a structure that can obviously grow. But here's the thing. If we're dealing with the leftmost variable, do we care what happens to the other variables? Yet. No, we don't care. So do we want the data structure to grow in the right direction? In the direction to the right? But here's the thing. We're adding the right-hand side of this rule right here going left. Because at this point right here, the stuff on the right of it is exactly the same. It never changes. But the things on the left of here may change. Not the terminals, but right here, so right here is where I mean. So this vertical bar, the things on the right stay the same. We're never changing those. But the things on the left corresponding to the variable do change. Okay? So that must mean we need a data structure that can grow and shrink in one direction only. What data structure is that? Where we can put stuff on the top, but can only take things off the top. A stack. So that's the structure that we'll actually pursue. And it seems reasonable because we're looking at a leftmost derivation. So these things used to be called pushdown stores back in the olden days before the fancy name stack came into being. So the name pushdown actually stuck. And because it's a machine model, it's an automaton like a DFA, so it's called a pushdown automaton. So a pushdown automaton, or a PDA. Note, it's not a public display of affection, although I wish it would be. It's a pushdown automaton. So here's what we need to think about. Let's think about what this machine really needs. It definitely needs a stack because of our reasoning earlier. And it needs the 5 pieces of the machine model for NFAs or DFAs that we had before. So, in fact, it's a 6 tuple. So is a 6 tuple. So Q, sigma, and now here comes the change, gamma, delta Q0F. So it's a 6 tuple. Can you tell me what Q is? Or can infer what it is? Not variables. It states, yeah. So Q states, sigma, what do you think sigma is? Alphabet. Skip over gamma for now. Delta, we're going to deal with the specifics of it, but what is it in general? Transition. Q0 is? Start state. F is? Set of final states. Perfect. So we obviously got to deal with these middle 2 pieces. So Q, sigma, Q0F are as in a DFA or NFA. Doesn't really matter in this case. And then we got to stipulate things on the gamma and delta. So gamma is a finite, in this case, stack alphabet. Okay. Why do we have a different alphabet for the stack? Couldn't I just say the only things you can put on the stack are the things on the input alphabet? What? It's not variables, but it's really to allow you to have generality. And in some cases, actually, you do need more characters on the stack than you have characters in the input. So you do actually need it. But it's really for generality, for allowing you to put whatever you want on the stack. So let's turn now to the transition function. Well, now we got to be a little bit careful because we got to think, okay, we got a stack now. We have states and input, so we know how to deal with that. We just got to know, how should we deal with the stack here? Well, let's see. What are stack operations? Push and pop. Those are the only two? Peek. So should we have 3 operations? Well, push and pop are absolutely necessary. There's no way to get around that. Can we get peek or avoid using peek if we can? Well, could we do this? Push a symbol on, then pop the exact same symbol off. Well, here's the thing. Do I know what was at the top of the stack at that point? If I push something on and then pop that thing I just pushed on back off, do I know what was at the top before? No. So what could we do is we can pop first, then we know what it is, and then push it back on so that the stack's contents remain unchanged. Okay? What do we need to be able to pop like that? We need something, but we're not going to actually do that. And we're not even going to have an empty stack operation either. So what do we do? Yeah.
I'm confused. Why do we need to see the next?
Well, we want to see what's on top of the stack, and we're trying to avoid just having an operation that looks at the element directly and doesn't do anything to the stack. Yeah.
Whenever you push onto the stack, can you like save what that was in another variable?
The issue is if I push a symbol on, then I have no way of knowing what was on the stack previous to that push.
But every time you push, you update whatever is on the top.
Well, if I'm pushing, I'm putting something there, so I am updating it.
Oh, okay.
So here's how we're going to do it. We're going to build it into the transition. And the way we're going to do it is you can only take this transition if you can pop this. Okay? So if you can pop here, then you can take this transition. Does that sound deterministic or non-deterministic? Well, deterministic to a point, but what if I have 2 transitions that go out on the same popped symbol? It's not deterministic. And in fact, we'll need some transitions that don't push or pop. So we have to have an epsilon transition for those. But let's get to a more interesting question, in my opinion. Well, if we're going to build this into the transition, well, one of those 2 operations has to occur first. Either the push must occur first or the pop must occur first. Which one should occur first? So let's just say we want to push X and pop Y. Well, can I push the X if Y was on top of the stack? If I can just push X, could I push it on a stack? Yeah, but how do I pop the symbol that's not on the top anymore? That seems problematic. So which of the 2 operations should occur first? The pop. The pop should occur first. Okay? Well, should we allow ourselves to not pop on a transition? Yeah. We should allow ourselves to be able to not pop if we don't want to. And in fact, is actually necessary in some cases. And same idea with push. Maybe we don't want to push on a stack. Maybe we're tired that day or something. We don't want to push on the stack. So I think we have everything we need. We want to be able to push and pop. We want to be able to not push or not pop, as the case may be. And the pop should occur first before the push. Sound fair? Okay. Well, before with NFAs, what pieces of information did we need to know to be able to execute a transition, just with an NFA? The current state, and then what else? Input, or in the case of NFA, the empty string. So in this case, we're going to go from the set of states, and then the next part is a member of the input alphabet, or the empty string, in the case of an epsilon transition. But we better do this at this point right here. We better do the pop before the transition takes place. Because if I try to do the transition and then do the pop later, then we might be stuck. Because we may not be able to do the transition in the first place. So we better do the pop right here. And the way we're going to say it is we can either pop, which is a member of the stack alphabet, some character, or we could not pop on that transition. We have an off day that day. Okay, so this corresponds to popping. But after the transition takes place, then we can push. Because after the pop takes place, it doesn't matter what's on the stack. I can put whatever I want on the stack without any fear of retribution from the stack authority. So, okay, great. Well, what did the NFA's transition function take us to? Another state. Well, another state or another set of states for an NFA. Well, if we want this to be a non-deterministic device, we better go to a set of things too. What did we annotate that with when we did NFAs? Instead of just Q on the right side, what did we say? Go to some subset of states. Power set of Q. So we're going to go to the power set of something, and we're going to go to Q times then the part corresponding to push. So this second piece is for push. And the good thing is, this is the last time we're going to deal with formal notation for PDAs. But we got to get a formal notation in there. So from now on, we're going to do diagrams, thankfully. I hope you're thankful for that. Okay. Any questions about the formal notation itself? So, yeah, go ahead.
So in the notation, the pop and the push look the same. It's just the position where it is.
Yeah. So what will be the second part of the transition corresponds to the pop, and then the third one corresponds to push. We'll see an example of what that looks like. Yeah. So when we write it out, the pop occurs first, and then the push. Yeah.
How does the gamma specify that you're doing push?
We'll do an example, and you'll see it. So the way we'll do it, it'll be pretty simple from how it looks. Other questions, though? Oh, one more thing. So when we looked at NFAs, or DFAs for that matter, how did we accept? So if we went to a final state, and what was the condition to accept?
That the string is open.
The string was fully read, right. What about here? Well, we probably should have the input fully read. What about the stack?
It should be empty.
It would make sense to make it empty, but we're actually gonna not require you to make the stack be empty. You could, without loss of generality, and we'll do this later, have a way to make the stack become empty, but the only thing that matters is that the input's fully read to accept. But we don't care about the stack. You can leave a mess on the stack if you want. But the PDA always starts with an empty stack. So it starts empty, but it may end non-empty. I should probably say that. So stack always starts empty, but not required to end empty. Fair enough. Okay, yeah, go ahead.
So the stack is not empty. How do you know
How do I know what?
You read the whole input.
The machine handles that for us. So it'll if you end in a if you're in a final state and you haven't read the input, the machine will definitely not accept at that point. It's just like with an NFA. If you're in some final state and you haven't read the input, you can't accept at that point. It's the same idea. But do we have a stack is empty operation here? I actually mentioned whether we do or we don't. Do we not? Yeah, we don't have one. So we better have some way of, it might be useful, although not required, to have a way of saying, oh, this is the thing at the bottom, because we don't have a way of knowing. Okay, so let's actually do an example. So what is our favorite non-regular language at this point? Or one of them. Number zeros and ones are the same. I'm going to actually make it a little easier and do 0 to the n, 1 to the n, which is a subset. Oh, great exam question, although it will not be on the test. If I have a language that is regular and I take a subset of it, is the subset regular? It's not. Take the language to be sigma star. Is a non-regular language a subset of sigma star? Yeah. So just because one language is a subset of another doesn't imply the regularity of the subset. Okay? So I was about to say that this is a subset of the number of ones and zeros being the same language, and both of them are non-regular. Just because it's a subset doesn't imply anything. Okay, just so you know. All right, so we have this language, and we want to make a pushdown automaton, a PDA for it. Well, can I make an NFA for this language? No, because it's not regular, and we proved that. So we better use the stack in some way, because, oh, here's actually a pretty interesting thing. What if I have a PDA and all the transitions do not push and do not pop, so do nothing with the stack at all? What is the language of that PDA?
Regular.
Regular. Because it just behaves like an NFA at that point. Okay? So with this language then, we better use the stack in some non-trivial way. Okay? That seem reasonable? Any suggestions on how, at a high level, we should use the stack here? So if the input has a bunch of zeros on it, and then a bunch of ones after it, how can I use the stack to, yeah, go ahead.
Whenever you see 0, add it to the stack. Whenever you see 1, remove 0 from the stack.
Perfect. A+. So whenever we see a 0, put it onto the stack. So as we're reading zeros, the stack is going to grow. Whenever we see a 1 after that, let's pop the zeros in tandem, and hopefully at the very end, everything matches up. Here's the problem, or a problem. What if we have an empty stack at a certain point, and every transition out of this state pops on that transition? Yeah, pops the stack. What happens, do you think, to that machine? It hangs. So whenever you get, so just like a NFA, if you have no transitions to do, you're stuck. You can't go anywhere. Same thing here. If you, for example, if you are trying to read a 1 and pop a 0, but there's no 0 on the stack, you're stuck there. Okay? So what we should do then is detect in some way, oh, you've read all the input and you're done. So what we're going to do is we're going to put on a special symbol, and then, so that corresponds to the very bottom because the stack starts empty. So then we put something on, put the zeros on, and then pop them off in tandem. And then at the end, if we've read all the input, the bottom, that special symbol's at the bottom, and then we can pop it off and we're done. Seem fair? Cool. So let's actually make a PDA for this. So we got to have a start state, of course. So the first transition, well, if we're putting on that special symbol and not doing the 0, 1 business, should we read on that transition then, according to our strategy? No. Our strategy is, as we're seeing zeros, then we put zeros on the stack, and then when we read ones, we pop those zeros off. If we're just putting that special symbol on, should we read? No. So the first transition is going to not read, and then the way we're going to write putting something on is the first symbol after the read, which is the epsilon right here. The first symbol is for popping, and then the second one is for pushing. Are we going to pop on this transition? No, because if the stack starts empty, you better not pop. So I'm going to not pop here either. So it's read, comma, pop. So in this case, not pop. And then arrow, and then the special symbol. And the way Sipser does it is with a $sign. You can put any symbol you want there, but it has to match what we're going to do later. But it's just some symbol that's not epsilon. So the way that we write this is, it's read, or not read, pop, arrow, push. And that's the way that we're going to write PDA transitions. Okay? Okay, great. So we go to a state Q1. So let's have Q1's job be reading zeros off the input and then putting those onto the stack. So what is the transition here? First of all, is it a self loop? Do we know the number of zeros that we're going to see? Or could it be arbitrarily many? Arbitrarily many. So for that reason, let's stay here, because I don't know how long I'm going to do this process for. Okay, so remember, the goal is to read zeros off the input and push zeros onto the stack. So does this transition read? Yeah, what does it read? 0. So the transition is going to be 0. Is this transition going to pop? No. Well, the only thing I would pop is the $sign, and we don't want to take that off. We want to make money. We got to have money. Anyone know that reference? Okay. Guys aren't old enough. Okay. So what are we going to push then? 0. Do I have to push 0?
Yes.
Or could I push a different symbol? I can push a different symbol as long as it matches later. Okay? We put 0 because we don't want to be wasteful with the stack. We want to be nice to the input. Okay. Well, let's see. I'm going to actually do something that's wrong, and then we'll fix it later. So the thing that could happen is, well, we're reading zeros, and then now we got to switch over to the ones. Okay? So what we do next is we switch over to the ones. So we better read a 1. Again, this transition's wrong. We'll fix it. So we read a 1, and then what do we do with the stack at this point if we're reading a 1? We pop a 0. So we pop 0 off. Should we push anything? No, because if we push something on, the thing I want to pop is under the thing that I just pushed on. So I better not pop anything. And I better not stay at Q1, because then I could be reading zeros after ones, and that's not a good thing either. Okay, well, do I know how many ones I'm going to read off the input to pop off the stack? No, I don't know. So I better stay in Q2 and do the same idea. Just read ones off the input, take them off the stack in tandem, and don't push anything. Okay, well, if everything matches up, what should be left on the stack at that point? The dollar sign. So dollar sign's on the stack. So the way we detect it is we can pop it off the stack. Well, should we read anything after this point? No, because if the zeros and ones matched up, then we're done reading characters. So we better go to another state that's accepting and not read, pop the dollar sign off, and then, well, we could push something because we don't have to have the stack be empty, but I'm going to clean up after my mess. I graduated kindergarten. We clean up after our mess. So I'm going to not push anything. Leave nothing behind. Okay, so that seems reasonable. We put on the special character to know when to stop doing the last transition at the end. We put zeros on the stack as we're reading them, and then as we're reading ones, we pop them off in tandem. So if they have the same number, we match at the end, we pop the dollar sign off, and we're good. Okay? What's wrong with that one transition I did? What's our favorite string? Empty string. Is it in that language? Yeah, it is. Pick n equals 0. N equals 0. So that corresponds to the empty string. Does this machine accept the empty string? There's no chance. Because if you go over to Q1 and try to go your way down, oops, you're done. Is there a way we can fix this?
Epsilon transition.
Oh, epsilon transition. Well, let's see. If I try to say, oh, we're not going to read on that transition, and we'll just do that. Is that a good idea?
We could check the dollar sign. If the dollar sign is being popped in.
Well, here's the thing. If we... Oh, I see what you mean. The problem is when we get over to Q1, no matter what the input is, there's going to be a dollar sign there. Yeah, so we got to do something else. Well, we can't do this transition because we just changed the 1 to an epsilon because we can't read. I hope you can read. We can't read for this machine here. So we can't read here. But I can't leave the 0 here because we want to pop them off in tandem. So what should we do?
Read nothing, push nothing, and pop nothing.
Yep, read nothing.
I did it wrong, but
Yeah, I get you. So, so that's one way to fix it. Does this actually fix it? Well, let's see. The empty string works its way through, so that's fine. If we have a non-empty string, then we push the zeros on and non-deterministically jump down and start doing the ones. So because it's non-deterministic, this is fine. Oh, so this actually works. Pretty cool. So I actually call this is just my notation, a triple epsilon transition. Because if you thought there was one epsilon transition, now you get triple. Pretty cool. Okay, any questions about the P? Yeah.
How does it fix it again in the case of the empty string?
Yeah. So I'm going to put in red what we had before, which is 1, 0, epsilon, because there's no way through the machine that avoids reading. So that's why we have the issue. Mm-hmm. Other questions? Yeah.
I have a question. So a DFA, you can make a DFA for this language, but you can make a PDA for this language.
Correct.
So does that mean a PDA is more computable than a DFA?
It has more computational power, yes. So the stack actually is really useful here because it allows us to, So we can avoid using the stack if we want to. But if we use the stack, we can get non-regular languages like this one this way. Because the stack can grow arbitrarily big. Whereas the DFA has a fixed set of states, it can't make more states as it needs it. So that's why we can get a non-regular language pretty easily this way. Okay? Yeah, go ahead.
With the empty string, when you still have to read 0, because you're in Q1.
No, so good question. So for the empty string, if we go from Q0 over to Q1, realize that it's a self loop. So notice that there is a way for it to accept. Yeah, so as long as there is a way for it to accept, it'll choose one of those ways. Yeah, so notice that if we have a non-empty string, for example, then we could take the self loop if we wanted to, or go down. So there are two choices we can make. It's just that because it's non-deterministic, this makes it a lot easier. Okay?
I forgot there was that option.
Yeah. So I think this is fine for now because the next thing will take a little bit, but I have a few questions that I want you to think about here. So this is clearly a non-deterministic device. So first of all, can you think of a deterministic version of a PDA? And if so, are these non-deterministic PDAs the same as deterministic PDAs? We saw they were the same for regular languages. Are they true here? And it turns out they're not. Non-determinism really does give you more power than deterministic versions. And another thing I want you to think about is, well, if we want PDAs to be the right computational machine for the context-free languages, what do we need to show with respect to PDAs and context-free grammars? What do we need to show between them? Yeah, that we can convert one to the other. How would we actually do that? If I have an arbitrary PDA, how do I convert it to a grammar? If I have an arbitrary grammar, how do I convert it to a PDA? For the second one, from a grammar to a PDA, think of the leftmost derivation idea. Could we simulate the derivation on the stack itself? Okay? So I'll let you think about that after the test tomorrow, so I'll see you tomorrow.